Hello, this is Waka breaking it down. We have the class on the introductory class to logarithms for Algebra 2. So this whole time, like especially the last unit we did with exponentials, we were talking about if you have an x in the exponent like you're trying to solve for. So for example, let me write out an equation here at the top for you, just something real quick, like if I had 10 equals 5 times 3 to the x, and we had some exponent unknown, right? We have a variable up there we're trying to solve for. Up until this point, we've said that you have to graph that out to try to look for the solution. But using logarithms, we're going to be able to solve this equation. So that's just one of the many things logarithms do. I teach statistics as well. And in statistics, if you have data that's kind of skewed or some curved data, you can take the logarithm of the x or the y values, and a lot of times you can straighten that data out. Data that used to be curved, you can straighten it. It's really important in statistics. Um, Whenever, like in the old days, when people before calculators and stuff, people like at NASA and stuff used to use logarithm scales in order to quickly multiply things together and stuff. So they have many, many uses. Mathematically, a lot of uses. So this is just the introduction to it. We got many classes and many lessons on how to use them and what they are. Let me give you, before we get into this whole activity, um, I'm just want to give you the rundown on what a logarithm is. This is something I wrote on the board before in the past and took a picture of, but it really is kind of a nice summary of what we're talking about. Um, a logarithm is just the inverse of an exponential. So, we've talked about inverses before. Oops, that's not what I wanted to do. I don't want to zoom in and out. Okay, so we've talked about inverses before. If I have a x squared and I want to undo that, I would just take the square root of it, and that would be an inverse, right? Same thing with a logarithm, kind of. You're undoing something. So if I have 10 to the third, let's say, and I take a log base 3 of that, like I'm doing a log of that with the same bases. This is base 3 and this is, sorry, not base 3, base 10. So if this base is the same as this base, then they're considered to be inverse functions of each other. What does that mean? Well, like we said before, whatever's up in this power, no matter what it is, will always come out. So this is going to drop out a 3. So they're inverse functions to exponentials, and that's how we're going to use them. So let's take a closer look at some examples here. So on the left, you see in blue, we have 1,000 equals 10 to the third, etc., right? 100 equals 10 squared, 10 equals 1, blah, blah, blah. I want you to notice that the numbers on the left are exponential numbers. Whoa, I didn't want to move that. Right? Whoa, sorry, this is touchy. Maybe I should have used a different format here, but um, those are exponential. If I were to graph those out, think about it, it would go like, if I made a graph over here on the right, it would start off 1,000, it would quickly go down to just 100, and then it would go 10, and then 1, and then a tenth and a thousandth, and it would get really small really quick. So you'd have this exponential function, right? That's what all those blue numbers on the left would look like, all these numbers, if I were to just start graphing them out, 1, 2, 3. But you'll notice something. If I change these into exponent format, like 10 to the some power, like some kind of power. So 1,000 is the same as 10 to the third, right? We know that. 100 is the same as 10 squared. 10 is 10 to the first. 10 to the 0 power is 1. We know that. And then 10 to the negative 1 power, remember we flip it. So it's 1 over a positive, or 10 to the positive 1. And 10 to the negative 2 switches, again, it's 1 over 10 squared, which of course is 100. So 1 over 100. So what I want you to see, you see how these exponents have become linear numbers. They're linear. It just goes 3, 2, 1, 0, 1, negative 1, negative 2, negative 3. It's just very, very linear. The exponents are linear, even though these numbers are exponential. Sorry, if you hear some noises, I'm at my hotel doing this video, and there's a lady in the background vacuuming right now. She just started. So sorry about that if you can hear it. So they're inverses. So what does that mean? Well, let's take a closer look at these numbers in red right to the right of that. So I said if I do the log of this, it will kind of undo it, right? So the log base 10 of 1,000, and I don't have to write it as 1,000, I could write it as 10 to the third. So what the logarithm is doing for us is telling us what this exponent is. It's saying what would be the exponent if I used this base on this number, right? So base 10, well, 10 to what power gives us 1,000? Well, 10 to the third, right? There's an easier, kind of a different way of looking at this. We call it rolling the log. I look at this base and I ask myself, the answer is the power, so 10 to the third power, that equals what was inside. So we call that rolling log because it looks like it's a logarithm, so that's why we say log. But we roll it because it's like the base to this power equals what's inside here. So that's a good way to look at it. So if we have 100, we could write that as 10 squared, right? So if I took the log base 10 of 10 squared, it's just going to spit out a 2. Well, why? Well, because 10 to the second power, 10 to the second power equals 100. So it just keeps going, right? 10 to the first power is 10, 10 to the 0 power is 1, 10 to the negative 1 is 1/10. So it's the same things we were talking about over here, right? These numbers and these exponential numbers, right? Those numbers. But you can see how it's different now because I've taken the logarithm. So these numbers, the answer to all these, those are the exponents. So you're just writing down the exponent. What exponent is that, right? For any particular base. In this case, it's base 10. So you can see all these numbers inside the parentheses are all what you get if you take 10 to some power. So let's look at a different format. What if it isn't 10? So on the right here, we have in black here, we have a base of 3. 27 is 3 cubed. 9 is 3 squared. 3 is 3 to the first. 3 to the 0 is 1. 3 to the negative 1 is 1/3, etc., right? So this is no different than what we did over here in blue. So I'm just rewriting this. Why? Well, I want to see what the powers are. Well, in this case, they're the same powers. But what's different? Well, I have a different base now. This is base 3. So when I do the logarithms, right, when I do the logarithms to kind of undo this, I have to use the same base. So 27 can be written as 3 cubed. So in order to keep this as an inverse function, I have to use the same base here as whatever is here. So those two bases have to be the same. So if it's base 3, I'm going to use base 3. Log base 3, right? So if I do that, then the exponent becomes the answer. Let me look at it a different way again. When we roll the log, you can ask yourself, this base, 3, raised to this power, 3, equals this number, which is 27. Let's look at another one. If I go 3 raised to the first power, I will get 3, right? And etc. You can see all these. 3 to the second power is 9. 3 to the 0 power is 1. 3 to the negative 1 is 1/3. So it's kind of undoing an exponential. Does that make sense? Like we're doing an inverse of an exponential. So 3 to the negative 2 is 1/9, right? These are so the work you've put in working with your exponential values is going to pay off, and working with negative exponents and all that work that we've done hopefully will pay off this unit. All right, so you can have any base you want. You can make up any base. Log base 2, log base 27, log base 57, whatever. You can make up any base you want. Now, we use common ones. And by the way, if there's a log that doesn't tell you what the base is, it just looks like log and nothing's written down below, that is automatically a base 10. And the reason is because base 10 is like the most common one you could have. We use base 10 for almost everything, unless there's a reason we don't need to. You'll see on your calculator, sorry, I'm just pulling this up so we can look. Don't worry about this. I'm just showing you what, whoops, let me put in a calculator function here. Sorry, this is jumping all over the place. Okay, don't yeah. We just want to calculate. All I wanted to show you was that right over here on the left-hand side of your pad on your calculator, there's a regular log in blue. It says log. That's a base 10, and you'll see right underneath it we have 10 to the x. Those kind of go hand in hand with each other because they're inverse functions. The calculator's smart, right? We're mathematicians. We know what we're doing. You can see it right above that. We have x squared. And what's the inverse of x squared? Well, square root. So that's why we put the square root right next to it, because they're inverses of each other. On the left-hand side here, you see we have the hat. That means I can put any power I want on something, right? Well, what's the inverse of that? Well, that's the same power, but as a root, right? The same number, but as a root. So let's do some quick examples. What if I said 81, right? Or sorry, let me do it with the square. So 9. I'll take 9, and then I'm going to come hit this squared button. Boom, I hit the squared button, right? I get a number. What if I want to undo that? Well, you do the inverse. What's the inverse? A square root. Square root of, whoops, this. Oh, geez. Holy Toledo. Okay, square root of that is 80, is back to 9, right? We started with 9, we squared it, then we undid the square, so we square rooted it, we did the inverse function, and we came back to where we started. Let's try it with some other power. What if I took, I don't know, 4, and raise it to the 5th power, right? I get some number. Again, if I want to undo that, I would go to the root, and I would do the 5th root of this number, right? And I would go back to 4. So the 4 is kind of the base. The power and the root kind of undo each other in this case, right? Now let's look at the logarithm. So let's say I take 10 to the x. What am I going to take it to? I don't know. I could take it to anything I want. How about 5? Okay, let's do 5. That's log base, or that's 10 to the 5th. If I want to undo that, I would do the log of that. You can see I'm doing control for the blue stuff, right? I want to undo that. So down here, they give you the option. Well, what base do you want? It has to be the same as what you have here. Right, so I use 10, and then I just put this number in there, and it should go back to where I started, right? Or go back to what the power is, if you will. So it's different than these, right? These are roots and exponents. This is a power as kind of the base, like, and then or as your kind of amount, if you will, that you're putting into your equation, right? I put 5 into my equation. If I had 10 to the x, then 5 goes in there and you get some number. And then to undo that, right, I do the same base as this as a log, and I'll go back to that 5 that I inputted as an output. Okay, so they are still inputs, outputs, right? This is an input, I get an output, and then for the inverse, the output becomes an input, and then you get the output of 5 again, right? So they're just reversing things. It's different because now the input is an exponent, where before the input was like maybe the base, right? This was the input. So then the 5 became the kind of the inverse function of each other. The 5th power and the 5th root were the inverses. In this case, it's base 10 to some power, and the inverse of that is log with the same base 10, and that's the inverse of a 10 to some power. All right, so the buttons are there. You'll see on the left, we've worked with E before, right? Let's look at E. So if I hit that button E, let me just do like 2 or something. That's fine. Okay, and I hit enter. Oops, let me do it again with a decimal. So then I get a decimal out of it so you can see it. If I want to undo that, we're going to do something called a natural log. It's just ln. It's just a logarithm. And if I do the natural log of that and put that number in there, you'll see how it comes back to my 2. So my input was 2, right? My output is 2. So it's kind of that shows you that they're inverses of each other. And this was my intermediate step. But when I do the natural log of that, you'll go back to where you started. Now, what's a natural log? It's still just a logarithm. We write it a little different because it's kind of special. It's just for E only. But it's a lot. Before we talked about log base 10 of some value, right? But now it's going to be, it's still a logarithm, but instead of base 10 or base 2 or base 3, it's going to be base E. It's very specific. using this special value of e that we discovered last unit, right? So this whole log base e of x, we write it in shorthand notation as ln of x. So it's the same thing. These are equal to each other. Oops. These are the exact same thing, both of those things. All right. It's just a shorter way of writing it. Mathematicians are lazy. We like to write things in shorthand notation. Okay, so hopefully for a starter, remember this is day one, like minute number 3 or whatever, right? Don't worry so much about understanding everything right away, but you should have the basic idea that a log is an inverse of an exponential now. And when we're working with these, the exponent is the input, and the answer of the log becomes that final output when you do the inverse of it, right? So we're connecting these exponents to these answers, which are the same thing, right? Those are the same thing. All right, let's get to the activity, and hopefully it'll make more sense. All right, so you should have had this. You should have worked through it already as best you can. I'm not going to go through every single little detail, but I want to hit the main points, right? Some of the main points. So this is the Richter scale. Hopefully you kind of went through this and graphed some things out, and you see that you should get something like this. The whole idea on a Richter scale, right, is this is in microns, right? You can see this is microns. So it's like a little bit of movement. Like how much movement do you get? 100 microns of movement. What is that on a Richter scale? And you can see that goes up to like 2 or something. In our table, to get past 2, the microns of movement had to be really big. And you see a World War II bomb will move the Earth with 100 microns, right? So you can really work your way up. If you have like we had the earthquake, right? The Fukushima earthquake in Japan in 2011, that was a 9 on the Richter scale. So, we were talking about 100 for a World War II bomb. So that's very similar to like 1 billion micrometers, right? Or in other words, 1,000 meters. Like that's a really big movement. Can you imagine the Earth moving 1,000 meters? That's a kilometer. It's moving a whole kilometer, right? So that's why the earthquake, just going from like a 4.5 up to a 9 on the Richter scale makes such a huge difference, because we're talking about these are the magnitudes of the exponent. So let me connect that back to what we were talking about. These numbers over here, they look kind of linear, right? 0, 1, 2, 3, 4, 5, 6, 7. So if you look back over here, that's these exponents that we're talking about. We're talking about those exponents. That's what makes it so powerful and makes the real number is huge, but the exponent is just linear. So looking at these values, these numbers get really huge really fast, but the exponent is just linear. And that's why we use them. It's really hard to work with these numbers, right? Look at those numbers. They're huge. It's easier just to talk about the exponent, and then we can use logarithms to kind of solve and mess around with things, right? So this is what your graph looks like. It shoots off to infinity that way, I mean, it's not going to go to infinity because once we get up to 9 or 10 or 11, then it just gets crazy, right? The whole Earth is like moving by kilometers. It's crazy. Right. Someday ask me about the Fukushima, what my experience. I'll tell you all about it if you want. But it was scary. I was in school when it happened. Anyway, okay, so you should kind of go through all that. You hopefully this idea that it never. Oh, that's one thing you got to look at, right? We never cross the y-axis. This gets closer and closer and closer to the y-axis without ever crossing it. We already said that these are inverses of each other, right? So we know exponents will usually kind of come along the x-axis and then they shoot up like this. And we also have learned in the past that when you do an inverse, they reflect over the y equals x line. So this is the y equals x line. So what would this look like if I reflected over the y equals x? Like let's say this is 10 to the x power, let's say. Right? If I reflect that over the y equals x line, yeah, what's it going to look like? Well, it's going to look like this. It's going to come up this way, and it's going to shoot off this way, right? And these are going to cross the y equals x line here and here, and that would be an inverse. So what you're seeing over here is a logarithm That's the inverse of an exponential. So remember, in the past, we said that the horizontal axis was the asymptote for an exponential. Now we're saying, because it's an inverse now, and because it goes this way, now we're saying the y-axis is the vertical asymptote. So the asymptote used to be horizontal, now it's vertical, because it just got flipped with everything else when we did the inverse. Okay, hopefully that all the stuff we've learned in the past just comes back and supports your understanding of what we're doing right now. All right, so that's number 3, right? Never crosses the y-axis. You'll never get an x value 0. It doesn't make any sense um, because of that asymptote idea, right? It looks kind of like a square root, doesn't it? It's not, but it kind of looks like that kind of idea, right? So hopefully you've gone through all this. Let me go back to the original here. So you graphed it out, answer all these questions, kind of get a good idea what the shape of a logarithm looks like, start to understand that it's an inverse of an exponential, so therefore the look kind of matches that reflection idea, right? Okay, so number 7 is like, well, let's graph it out, right? So hopefully you go and you graph log x on Desmos, and you try to do all the things it tells you to do, following the table idea, and you go through all that stuff, hopefully, and then hopefully you ended up with something that looks like this, right? That's what the real logarithm looks like. Um, these are the same points on the Richter scale that you were looking at up here. It's just that we put the logarithm on top of it now. So you can see that really it is the log base 10, right? So 10 to some power and log base 10 are inverses of each other. And again, remember, I don't have to write that 10. If I just said log x, you would have to know it's log base 10 automatically. But you can write in the 10 if it helps you remember what it is. Okay, those are inverse functions. All right, so number 8. Now we're working with different, or just kind of working with the numbers a little bit. You can see that none of the negatives make any sense. None of the negatives make sense, but the positive ones do. You can use even a decimal. That's okay. Decimals are allowed, right? Why is a decimal allowed? Well, 0.1 is the same as 1/10, isn't it? And we saw that 10 to the negative 1 power would equal that. So negative 1 power would equal 0.1, which 0.1 is the same as 1/10, right? So this is the power down here. 10 to the 0 equals 1, 10 to the first equals 10, 10 to the second equals 100. So, like, what power of 10, I'll put a question mark here, would equal 0? Well, there's no such thing, and that's why this is all like undefined and doesn't make any sense, because there's nothing I can go 10 to this power and get it equal to 0. There's just nothing that's going to do that, right? It just isn't going to happen. Same thing with negative 1. There's like no power I could come up with where this would equal negative 1. I can't change a positive into a negative just by putting an exponent on it. It's not going to make any sense. That just will never happen. So that's why you see these are all like undefined. It just never happens. And then when you look at the graph, like we said, it's kind of shows up on the graph because you have this asymptote. And there's nothing over here, right? There's no part of the graph that shows up on the left-hand side for negative x's. It just wouldn't happen. There's no such thing, right? So that's why things look the way they look. That's why we have the numbers we have. Okay, x-intercepts, yeah, well, we got that here. That's not a problem. That's where the y value is 0, right? Y-intercepts, we don't have any because we have an asymptote, right? What's the vertical asymptote? Well, that's the y-axis, so that's x equals 0, right? All these things should kind of match up to what we're thinking and talking about. All right, what's the domain? Well, let's go back to this graph. You see how it goes from the asymptote here, and it doesn't touch it, so it's got to be bigger than 0, not equal to, and then this will just shoot off to infinity pretty much, right? It shoots off to infinity. So we'll just say, oh, you can just leave it like that. That's fine. But some of you like to say, oh, it goes to infinity. And that's okay, right? You can always write the interval notation if you like that better. That's more of a pre-calculus way of doing it, which is nice. You get used to that before you get to pre-calculus. Okay, whoops, I got my asymptote sticking there. All right, here we go. All right, so let's look at number 9. It's still the same thing, right? You're just getting used to 10 to the second power equals 100, 10 to the third power equals 1,000. And this is where we're rolling the log. Roll the log, roll your log, right? So when I look at this, I know this is base 10, even though it doesn't say it. So 10 to the third power equals 1,000. This rolling the log idea is very, very important. It's how you undo a log. It's how how we talked about solving an equation that has something up here that you don't know, right? The only way that works is if you can roll the log. So this rolling the log idea is extremely important. That's the whole idea behind a logarithm. All right, so let's look at some different ones. We worked with 10 a lot so far, right? So what if we have some different ones? Sorry, you can hear the worker at the hotel here. So what do we have to do? Yeah, so what we're asking ourselves is, what power do I need of the base 2 to make 16? So if I say 2 to what power equals 16, hopefully you tell me that it's 4, right? 2 to the fourth power, 2 times 2 times 2 times 2, that's 16, right? 3 to what power, again, roll the log, right? 3 to what power equals 9? Well, hopefully you say 2. 3 squared equals 9. So the answer is squared. Remember, these are the exponents. The answer is the exponent. 5 to what power equals 125? Well, 3. 2 to what power equals a half? -1. 4 to what power equals 0? Oh, that's impossible. There's no number that I can take 4 to have it equal 0. It's not gonna happen, right? And then we have an easy one. 10 to the first power is 10. All right, so this is on number 11. We have a base 2 here. I'm always looking at that base because that's kind of it's the base of what's going on. No pun intended. Well, maybe a little pun intended. All right, so here we go. 10 to what power? Like, all of these are the powers, right? 10 to what power equals this number, right? Well, 2 to the -2 equals 1/4, right? Because the negative flips it over. 2 to the -2, right? The negative flips it over, and then we have to go 2 squared to get 4, right? So that's that. Same thing for the rest of these. 2 to the -1 is 1/2. 2 to the 0 is 1. 2 to the first 2, right? 2 squared is 4. 2 to the fifth power is 32. So you're just filling it in. Notice that the logarithm equals the exponent. The logarithm equals the exponent. All right. So what's going on here, right? There's some context that you have to kind of work your way through and understand. So what do all these mean? Well, number 1 says h of 8. So if I put 8 in for x, right, that would be like what is it? So sorry. So x is the weight, right? So this is after midnight, right? Yeah. So after midnight. So if we put in a weight of 8 into x, then our answer would be 3. So that means 3 a.m. because it's 3 hours after midnight. If I put in 1, in this case I'm putting in 1, right? You have to know your notation for functions. If I put in 1, I'm gonna not have anything, right? So it's gonna be midnight, right where we started. If I put in a quarter, that's like here. Well, that's like 2 hours ago, right? That's 2 hours ago. So that would be 10 p.m. instead of midnight, right? Okay, let's move on. Part C. So we're graphing this now. All those points that you had, you're just graphing them. Notice it's base 2 now instead of base 10. And these are all inverses, so it's not like you can say this is the power or whatever. It's more like this is the power, I guess. Yeah, like this becomes my power now. So you can almost think of it like, let's do it that way real quick, just so you can see me talk about it that way. So this is base 2, right? And I'm putting in value. So if I say 2, remember this is equal to y, but 2 to the y equals x. This is rolling the log, right? Really important. This base 2 rolled to the y power equals that inside thing. That's rolling the log. So if I kind of keep that in mind, notice that this looks like the input is y and output is x. So if I go 2 to the 0 power, I get 1 here, right? If I go 2 to the first power, but I'm talking about a 1 on the y-axis, that should equal 2 on the x-axis. Do you see how things are they feel backwards from the exponentials? If I go 2 to the second power, but the second I'm talking about is on the y-axis. 2 to the second is 4, but now it's 4 on the x-axis, right? So the x and the y's are kind of backwards, right? If I do 2 to the third, right, that's 8, but I'm talking about 8 on the y, or 8 on the x, right? 2 to the fourth, 16, 2 to the fifth, that's 32, right? So the x's and the y's have been switched. Why? Well, because we're not graphing the exponential, we're graphing the logarithm, and the logarithm is the inverse of the exponential. So the x-axis and the y-axis have just switched, and that really is a good kind of insight, right? The x and y are just switching, right? So all those points kind of just switch x and y's when you were working with an exponential. All right, so then you can do all the different coordinate stuff here and answer all these questions, right? So what appears like the domain, we've already talked about that. It's bigger than 0, all real numbers. The vertical asymptote, that's at x equals 0. We already talked about all that stuff, right? So hopefully none of that is kind of more than what I've already talked about already. So hopefully that gives you a really good start on logarithms, gives you a good idea of exponentials and logarithms are inverses of each other. So the x and y axis have switched, and you really need to start understanding the different bases and also rolling the log, right? Rolling the log is super important to be able to kind of make sense of what's going on with all this stuff. Okay, so happy studying and just give it your best.